Start.
Section 6.3 matrix algebra. Well, we already have seen some matrices. We know how to calculate determinants. Now, what else can we do with matrices? Let's imagine that somebody gave us two matrices, matrix A and matrix B. They do have same shape. Same shape means that they are looking like a same size rectangle. 1, 2, 3, 4, 5, 6. That's matrix A. And matrix B is going to be 1, 0, 1, 0, 1, 0. So you see that there are two rows and three columns. 2 rows and 3 columns. So they're looking same. What we can do with matrices? Well, first we can add or subtract them. So we can do A plus B. How do we add two matrices? Like we add vectors. So we add terms which are sitting on the same spot together. For example, here we have term 1 and here we have term 1. We add them together, get 2. We have 2 here and 0 here. We are going to get 2 again, right? 3 plus 1 is 4. 4 plus 0 is still 4. 5 plus 1 is 6. And 6 plus 0 is still 6. So that's a sum of two matrices. We also can subtract them, A minus B. What is subtraction? Well, basically you do same. You just, instead of adding numbers, subtract them. So 1 minus 1, 0. 2 minus 0, 2. 3 minus 1, 2. 4 minus 0, 4. 5 minus 1, 4. And 6 minus 0 is 6. So addition, subtraction, clear, right? We also have something what we call zero matrix. Zero matrix can be any size, and you can just like make up a zero matrix of the same size you have over here. So it's going to be 0, 0, 0, 0, 0, 0. Why do we need zero matrix? Zero matrix is a nice matrix which you add to matrix A or matrix B and gonna get matrix A or matrix B back. So what I'm going to do, I'm going to add A plus, I'm going to label zero matrix as Z. Okay, normally they put 0 here, but if I put 0, it's not going to look nice. So, for example, 1 plus 0 is going to be 1, 2 plus 0 is still 2, 3 plus 0 is 3, 4 plus 0 is 4, 5 plus 0 is 5, and 6 plus 0 is 6. So, zero matrix added to any matrix is going to not change it, like with normal numbers. And same is going to happen if you put zero matrix first and your matrix next. Just make sure that zero matrix looks same as your matrix. Okay, next interesting thing, we can multiply matrix by a number. Let me explain you how the rule is going to work. Let's imagine that we want to take matrix A and multiply it by 2. Write down 2A. How it's going to work? We're going to multiply by 2 every element of a matrix. So 1 by 2 is going to be 2, 2 by 2 is 4, 3 by 2 is 6. 4 by 2 is 8, and 5 by 2 is 10, and 6 by 2 is 12. We can multiply matrix by any scalar, by 2, by 3, by negative 5, and that's going to mean that you multiply every element by this number. Now, the hardest thing with matrices is how to multiply two matrices. It's going to be a little bit longer than addition, subtraction, and zero. So what I'm going to do, I'm going to erase everything and do a special kind of consideration for product. To multiply two matrices, we're going to start with multiplying two very simple matrices. I'm going to introduce a row matrix. Product of matrices. And we are going to start with introduction of row matrix. Row matrix, it's matrix which is looking just like one row. I'm going to take the first row of my matrix, and that's going to be a row matrix. So row matrix is just one row. Column matrix is going to be just one column. I'm going to create one column from nowhere, and this one column matrix is going to be like, for example, 1, 2. So two matrices, a row matrix and the column matrix. What are we going to do? We're going to try to multiply a row matrix by column matrix. The requirement for them is to have them of the same size. For example, these two cannot be multiplied. I'm going to extend this one a little bit to make it like possible to multiply. I'm going to change the numbers here. It's going to be 1, 3, 0. So the rule is going to be next. If I want to multiply row matrix by column matrix, the result is going to be a number, which is going to be multiplication of the first element of row and column 1 by 1 plus 2 by 3 plus 3 by 0, which is going to give me 1 plus 6, which is going to give me 7. Okay? So the product of this row matrix and column matrix is going to give me 7. We're supposed to make sure that to make this formula working, we're supposed to make sure that we have the same amount of elements here and here. So it's 3 elements here and 3 elements here. Otherwise, you know, you're gonna end up with missing element either here or here if you have different number. Okay, now let's consider our two matrices A and B. Matrix A is going to look like this. That's our old matrix. 1, 2, 3, 4, 5, 6. I'm going to change a little bit my matrix B. That's not going to be the first matrix B we had. It's going to be slightly different because I have the rule about size of the matrix. I'm going to create a different one. So matrix is 0, 1, 3, 0, 1, 1, 1, 0, 1, 2. So I'm going to multiply these two matrices using next rule. For the first element of the matrix, I'm going to multiply the first row and the first column. Okay, so it's going to produce element C11. The final matrix is going to be labeled as C, and that element is going to be labeled as 1, 1. So it sits on a row number 1 and column number 1. How I'm going to calculate it? Well, I'll need some additional space to calculate it. I'm actually going to use this rule. So I'm going to multiply 1 by 1, 2 by 3, and 0 by 3, which is going to give me, I already know it's going to give me 7. So this element is going to be 7. I'm going to maybe put 7 over here. Now, for the next element, C21, the second row and the first column, I'm going to multiply the second row by the first column. Exactly I was doing it over here. So I'm going to multiply 4 by 1, I'm going to get 4. 5 by 3 is 15, so it's going to give me 19. And I'm going to just write down 19 over here. Now, I'm going to move to my next element, C12. And for C12, I'm still going to multiply my first row because it sits on the first row. But because it sits on the second column, I'm going to change it to second column. I'm going to multiply this one by this. So it's 1 by 1, 2 by 1, and 3 by 1, which is going to give me 1 plus 2 plus 3, which is going to give me 6. C22 is going to be a second row and a second column. So actually, element is going to sit on the intersection of these two. So this one and this one are going to intersect at element 2, 2. And because I'm still multiplying by 1, 1, 1, I'm just going to add these numbers, 4 plus 5 plus 6, right? 4 plus 6 is 10, and plus 5 is 15. And the next one is going to be C13, the first row and the third column. So I'm going to multiply my first row, 1, 2, 3, by column 0, 1, 2. So 1 by 0 is 0, 1 by 2 is 2, and 2 by 3 is 6. So I do have 6 plus 2, which is 8. And the last element is going to be 2, 3. And, well, I'm going to multiply row number 2 by column number 3. 0 multiplied by 4 is 0. 1 by 5 is 5. And 2 by 6 is 12. So I'm going to get 17 over here. So that's going to be my resulting matrix. Normally, we don't write down C11 equals. Usually, we just write down 7, 6, 8, and 19, 15, 17. That's what I'm going to do to kind of summarize the result of multiplication. 19, 15, 17. What is important to remember when you multiply two matrices? Because of the process of multiplying pairs, one from row, one from column, you're supposed to make sure that this size of the matrix is same as this size of the matrix. For this size and this size, it's not important. It can be two rows, two rows, 1, 2, 3, whatever. As same over here. You can have as many columns as you wish, but the size of the column is supposed to correspond to the size of the row to make the process working. So what I want you to do, guys, I'm going to give you two matrices to multiply on your own, and maybe I'm just going to switch these two matrices. Why not? Let's see what is going to happen. Instead of actually giving you this multiplication process, it's going to be too long, I guess. So imagine that somebody tells you, okay, multiply B by A. Can you guys try to do this for like 2 minutes? And I'm going to count to 5. 1, 2, 3, 4, 5. Now I'm explaining why it's not possible to do this. I'm going to write down matrix B. 1, 3, 0, 1, 1, 0, 1, 2. And then matrix A, which is 1, 2, 3, 4, 5, 6. Remember, the process is to take one row and multiply by a column. When we start doing this, you are going to multiply 1 by 1, 1 by 4, and 0 does not have a pair over here. So, unfortunately, this multiplication is impossible. So you cannot multiply B by A. So matrices are not interchangeable in the product. So usually if you set, well, some matrices are going to be interchangeable, but not all matrices, I would say. Okay? Okay, now I'm going to erase this and introduce identity matrix. Identity matrix is a matrix which is a square one, and it can look like this: 1, 0, 0, 1. It also can look like this: 1, 0, 0, 1, 0, 1, 0, 0, 0. So identity matrix is a square matrix of arbitrary size, whichever size you need, which is going to have 1 on diagonal and zeros everywhere else. What is interesting about identity matrix, and why do we kind of specify this identity matrix? If you multiply your matrix by identity matrix, you're supposed to get back your matrix. I'm going to do this with matrix A. My matrix A is 1, 2, 3, 4, 5, 6. And if I want to multiply matrix A by identity matrix, I'll need to make sure that my identity matrix fits to multiplication process. So, how big is supposed to be my identity matrix? Well, because I have 3 elements here, my matrix, a second factor matrix, supposed to have 3 elements. So it's going to be 1, 0, 0. Because I know it's supposed to be a square matrix, it's going to be 3 by 3 matrix. Okay? And I'm going to just do multiplication maybe for a couple of elements, and I'll ask you to finish it if you can. Okay, so let's imagine that I multiply my first row by first column. You see that only one element is going to be actually multiplied by something, only this one, the first one. And the other ones are going to be multiplied by zeros, so they're not going to change anything. That's going to be 1 by 1. If I want to try to find this element, I'm going to multiply this by the first column, and again, only first element is going to participate in multiplication. 2 others are going to be multiplied by 0. If you repeat this for the next column, you're going to see that next column is going to leave for multiplication only element 2. And if you do the second row, it's going to be element 5. And this one is going to leave element 3 and 6. So you see that you actually get exactly the same matrix. Well, identity matrix works like 1 in a real numbers world. So you multiply any matrix by identity, you get the matrix back. Okay. Next one is going to be inverse matrix. We do know that numbers do have inverses, right? Like we have number 3 and there is an inverse of number 3, which is 1 over 3. You multiply them like 3 multiplied by 1 over 3 and you get 1, right? In the world of matrices, the same relation is going to work. Just instead of numbers, we are going to have matrices. So we are going to have matrix A by inverse matrix, supposed to be identity matrix. We also know from numbers world that if you multiply 1 over 3 by 3, it's still 1. So we are going to require same for matrices. Identity multiplied, inverse multiplied by A is going to be identity. So if there is a matrix A inverse such that it satisfies these statements, it's going to be called inverse matrix. I'm going to circle it and call inverse. Does every matrix has inverse? We do know, for example, that for numbers, 0 does not have inverse. 0 has no inverse, right? You cannot put 0 in the denominator and say, okay, 0 multiplied by something is going to give me 1. Actually, it's impossible to make, right? For matrices, we also have matrices which do not have inverses. So not all of them are going to have inverses. I'm going to introduce how to find inverses of 2 by 2 matrices. And for bigger sizes, it's more theory to explain. So we're going to stick to 2 by 2 matrices, okay? And I'm going to introduce you a rule which is not in our book, because I think our book is a little bit too complicated to find inverse. We are going to just introduce a simple rule for 2 by 2 matrices. Okay, let me erase everything and I'll give you the rule and we will calculate inverse. So A inverse for 2 by 2 matrices. Imagine that we have matrix A, B, C, D. So how do we build inverse? Again, no explanation, no proof, but you can trust me. We're going to check it on examples. So in denominator, we are going to have AD minus BC. And the matrix is going to be D and A switched, and C and B are going to have negative sign. Well, very weird rule. Probably think, okay, why it's this way? We're going to check it, and you're going to see that it works actually. Remember, the condition for inverse matrix is a matrix which is making identity with matrix A. So if we can do this, well, that's fine for us. I think what we can do actually, in our notes, I actually just found inverse for some matrix, but here we can just check what is going to be the product of A and A inverse in this case. And if we are going to get identity matrix, I think that's going to be best proof that this method is working, right? So that's going to be the matrix. So let's see, I'm going to multiply A by A inverse. My matrix A is A, B, C, D. My inverse matrix is 1 over AD minus BC, and over here D minus B minus CA. Well, matrices are square, so it's two numbers here, and this one is just a number, so I'm going to put it in front. I'm going to start doing multiplication and keep this number outside, AD minus BC. So I'm multiplying this by this, right? So what I have, A multiplied by D and B multiplied by C, because it has minus, B multiplied by C is going to be this. For the next element, CD, DC, I have CD minus DC. You see what it's going to be? Well, it's going to be 0, right? For next element, AB multiplied by negative BA. So it's going to be AB was minus, this minus A, plus BA. Again, we're going to get 0. And the last element is going to be this column and this row. It's going to be minus CB plus AD. Now guys, I'm going to put zeros instead of these two elements. We already calculated them and we do know that they are zeros. So I'm going to erase them. I don't want to copy everything. I'm just going to put zeros instead of these two elements. 0 here and 0 here. Now I'm going to multiply my matrix by the number in front, which is actually kind of division, right? If you compare this one and this one, you're going to see when I multiply this number by this number, I'm going to just get 1. 0 is here, 0 is here. Do I get 1 if I multiply this number by this? Yeah, because that's actually AD minus BC or minus CB, so it's going to be 1 again. And I got identity matrix. So this method is working. You can just memorize it. It's not difficult. Here we have determinant of the matrix, right? You see it's AD minus BC. So diagonal elements are switched and counter diagonal elements are having minuses, okay? Maybe we should find one inverse matrix just like for like a little bit of like example. So what I'm going to do, I'll give you a matrix and I'll ask you to find inverse, okay? Not supposed to be too difficult, and I'll give you kind of a minute to do it, okay? So my matrix A is going to be 1, 2, 3, 4. I'm not very creative, but so I'm going to count to 5, and you can do inverse on your own, and then like use the formula, and then you're going to compare it to my inverse, okay? So 1, 2, 3, 4, 5. So I'm going to start making up inverse. So first, I'll need to do AD, BC. So AD is 4, BC is 6, so that's my number, right? Then I switch 4 and 1, 4 here and 1 here, and I put minus here and minus here. What am I going to get? Well, this one is negative 1/2, right? And that's 4, minus 2, minus 3, and 1. Well, what I can do, I can multiply this negative 1/2 by every element and kind of just get a matrix without coefficient. That's going to be minus 2, right? 4 multiplied by 1/2. This one is going to be 1. This one is going to be 3/2. And the last one is going to be minus 1/2. Doesn't look very nice, but that's how we find inverse. Now, the question is, why do we need actually inverses? Well, it's nice to know that matrices like numbers do have inverses, but why do we need them? Remember, our major goal in section 1, section 2, and section 3 is to solve system of equations, to develop a method which will generally allow us to solve them faster, not just like our regular substitution method, which is going to work for 2, 3 equations, but it's not going to work for systems of 1,000 or 10,000 equations. So let me explain you how works how inverses are working. How it's helpful to know inverse if you want to solve system of equations. Well, what I'm going to do, guys, I'm going to start writing system of equations in a matrix form. Let's consider that we have system of equations x plus 2y equals 1 and 3x plus 4y equals 2. That's actually my old matrix 1, 2, 3, 4. I just put a right side over here. So here I have matrix A, which is 1, 2, 3, 4, right? I also have, I can call it a column of x, and that's going to be x and y. And I also have column of B, which is going to be 1, 2. Now, guys, what I can do, I can write down this system in matrix form as A multiplied by x equals B. Is it going to work? Well, I'm actually going to show it once that this way is exactly what we have over here. I'm going to write down that 1, 2, 3, 4, instead of x, x, y, and instead of b, 1, 2. 1, 2. So, according to my multiplication process, I'm supposed to multiply this by this. So what is going to be 1 by x plus 2 by y, and it's supposed to be equal to the element here, the first element. Here, first element is 1, so I'm going to put 1. Same is going to work over here. It's 3 by x plus 4 by y, and that's going to be element 2 actually here, right? So the product is going to give me x plus 2y and 3x plus 4y. Because these two matrices are equal, means that this one is equal to this, and this one is equal to this, and I'm going to get 2, and that's exactly the same equation. Well, how it's helpful? Let me write down again this matrix equation over here. Ax equals B. So, if my matrix A has inverse, if A has inverse, then I can use this inverse and multiply by it both sides of my equation. Well, here I don't have any space to fit an inverse, but I'm going to put it here in front. What I'm going to have here, remember that inverse by matrix is identity, right? Identity by any matrix, it's a matrix itself. So here I'm just going to have x. What I'm going to have here, well, the product of inverse matrix and the column B. What is x actually? X is actually xy. What is this? Are going to be two numbers. Well, I'm going to call them number 1 and number 2. Well, you see that x and y are going to be kind of solutions of this system. So basically, if you accidentally do no inverse, then you just multiply it by right side and you get your answer right away. Well, I think I'm going to do it. What I'm going to do, guys, I'll need to erase a little bit over here. So I introduced a major idea, right? So I'm going to find actually x and y two ways. A standard way we use substitution and non-standard way matrices, okay? But I'm going to erase everything from over here. I'm going to keep the system on the board. And, well, for inverse, I'm going to, because we already calculated inverse of this matrix, I'm just going to kind of copy it from my notes. We have, let me see it, -2, 1, 3/2, and -1/2. That was inverse. So my matrix method is going to tell me that x, y are going to be equal to the product of A inverse by B, right? Well, my A inverse is -2, 3/2, 1, -1/2, and my B is just 1, 2. Well, let's multiply them and see what we are going to have for this. So first row multiplied by first column, which is only 1. It's -2 plus 1 multiplied by 2 is +2. This one multiplied by 2 is going to be 3. 3/2 multiplied by 2 is 3. And this one is going to be -1. Well, I got two numbers, and one of them is 0, and one of them is 2. And they are going to be my solution. So x equals 0, y equals 2. Well, in my notes, I actually just take these solutions and plug them over here. But I think instead of this, what I can do, I can actually just solve the system and see if these are going to be solutions, same solutions. So what I'm going to do, I think I'm going to multiply this equation by -2 and add it to the second one. So I have x, 3x minus 2x is just x, right? This one is going to give me 0, and this one by -2 and 2 is going to give me 0. Oh, well, I just got solution right away. To calculate y, I'm going to plug in x over here. Why do I have actually 2? Maybe I did a mistake somewhere. I was supposed to get 1/2. Yeah. Oh yeah, I got 1/2 in my notes, but somehow I got 2 over here. Let me see what I did wrong over here. I see. When I was doing multiplication, when I was multiplying it over here by 1, 2, I multiplied this accidentally by 2 instead of 1. So it's not 3 actually, that's 3/2. 3/2 minus 1 is 1/2. Sorry, did a little mistake, 1/2 over here. Now, I'm going to plug in x equals 0 here, and I'm going to get 2y equals 1 from where y equals also 1/2. Okay, so solution is matching. I mean, correct solution is matching. Well, what can be bad about this method of using inverses? First, it's not easy to find inverse, right? It's much longer to find inverse than just to solve this system. But for bigger systems and for stronger computers, maybe it's not that long. Second, not all matrices have inverses. Remember, even 2 by 2 matrices sometimes don't have inverses just because there is no AD minus BC. If this one is equal to 0, you're going to get division by 0 and there's going to be no inverse. So one category of matrices which are not going to have inverses are matrices for which determinant is equal to 0. Okay, so those matrices are not going to have inverses, but the system still can have a solution. So inverses are a good way to solve systems of equations, but not only one way. Okay, that's all for this section. Please do the homework. Thank you.